P divides A square, then P divides A. In the theorem statement it's given P is a prime number and A is any positive integer. If P is a prime number which divides A square, then P also divides A. Let us see the proof of this theorem. It's given in the theorem statement that A is any positive integer. So we know that any positive integer can be written as a product of primes. So A is equal to P1 into P2 into etc. into Pn, where P1, P2, etc. Pn are primes and not necessarily distinct. Let us consider 8. 8 is equal to 2 into 2 into 2. So if A is 8, P1, P2 and P3 are all 2. But if I consider 6, 6 is equal to 2 into 3. So here 2 primes are involved and these 2 are distinct. P1 is 2 and P2 is 3. Whatever number you have, you can write that number in this form. But in the statement of the theorem, it's given P divides A square. So we are interested in knowing what A square is. But if we know what A is, squaring A we get A square. A square equals P1 square into P2 square into P3 square etc. into Pn square. If A equals this, squaring A we get A square. Given in the statement P divides A square. If a prime number divides a positive integer or a square of a positive integer, then it means that P is a prime factor involved in the prime factorization of this number. So P divides A square means P is a prime factor involved in the prime factorization of A square by using the fundamental theorem of arithmetic. By the fundamental theorem of arithmetic, we know that any composite number can be written as a product of its primes. So, P divides A square implies P is a prime factor involved in the prime factorization of A square. But we know the primes involved in the prime factorization of A square are P1, P2, P3, etc. Pn. So P is a prime factor involved in the prime factorization of A square, but only primes involved in the prime factorization of A square are P1, P2, etc. Pn. By considering the uniqueness of fundamental theorem of arithmetic, we say that by the fundamental theorem of arithmetic is a unique representation of writing a number, a composite number as a product of its primes. So because of this uniqueness of this fundamental theorem, we say that P is 1 among these numbers. If P1, P2, P3, etc. Pn are the only primes in the prime factorization of A square, and if we say P is also a prime factor involved in the prime factorization of A square, P should be 1 among these numbers. P should be 1 among these primes. So, P divides A square means P is one of the prime factors of A square. But by the uniqueness of fundamental theorem of arithmetic, P should be 1 among these numbers. P, P1, P2, etc. are different symbols we use to denote prime numbers. So, P is 1 among P1, P2, P3, etc. Pn. So, we know that A is equal to P1 into P2 into P3 into Pn. But we have said just now that P is 1 among these primes. If P is 1 among these primes, then it means that P divides A. We know that we are able to write a composite number as a product of its factors. Then these are the numbers by which this number is divisible by. So, if P is 1 among these numbers, then P divides A. Firstly, we have written A as a product of its primes. These primes may or may not be distinct. After that, we have found out what A square is. So the primes involved in the prime factorization of A square are P1, P2, P3, etc. Pn. But it's given in the statement of the theorem that P divides A square. If P divides A square, then it means that P is one among the prime factors involved in the prime factorization of A square. But the only prime factors involved in the prime factorization of A square are these P1, P2, P3, etc., Pn. By considering the uniqueness of fundamental theorem of arithmetic, this means that P should be one among these P1, P2, P3, etc., Pn. If P is one among these, we have already written A as a product of P1, P2, etc., Pn. If P is one among these primes, then P divides A.